Okay, so we will end this part. Like next time we're going to talk about extractors with the Saks-Zhou algorithm. It's a magnificent algorithm, and I try to be more formal here because the God is in the details here. So this is an algorithm that puts BPL using Nissan's PRG in L to the 3 halves. Time-wise, it's better, by the way. It's open to get poly-n time also. You know, comparing to a BPL in SC that we just did, or sketched. But BPL is this thing, and that's from 90, like 4, 5, I don't know. You will see 97, but that's the journal version. So it's this thing. It's really old. 30 years open to move this. Actually, what they do. You have a question? I just put you. Okay. So what they do is they solve a different problem, which I'll just say why it solves this thing. They say, you know, if you have a matrix A, so there's no problem 6 in your homework, but more than you are expected to solve it, better. If you have a matrix A, it's stochastic. I don't know if I told you that it's stochastic in your case, because you don't need it. It's stochastic. Have a good karma with stocks next year. And it's W by W. And let's say that, and that's kind of important, that every entry is represented using T bits. Okay. And you want to approximate its nth power. So that's what you want to do. More precisely, you know, you're given I and J. You're not going to put the entire matrix there. You're given I and J, and you're asked, tell me this thing up to plus minus some epsilon. And Nissan is a way of doing that. You'll do it in the homework, by the way. That's your question. And you're going to do it if you haven't done it in this space. Don't do it better than that. You can try. I think you need, the T is also probably needs to be there or something. I'm not sure about where the T sits. But this is the space that you should have. Nissan does it without looking at the matrix. That's the cool thing. You're looking at the matrix in your homework, right? That's what you do. You look at the matrix and you take powers. Nissan tells you, I don't care about your matrix. I'm going to tell you things that you should do. And when you do that to your matrix, you will get the power. I mean, of course, you need the matrix. So what do I mean? What Nissan tells you, right, is that you know, for most HS, let's do this thing. For most HS, you know that it tells you something like my PRG, which let's call it Nissan from now because it's be nicer. Nissan, you know, given everything, given A and you know maybe accuracy parameter, delta parameter, whatever, but definitely the N that you want, in H. Anyhow, Nissan, when it gets the power that you want in H, it gives you, given a branching program. In H, it gives you, you know, what's the probability of getting from the start to the accept state, but it doesn't really depend on any of the states. It works for all states. You can just designate another one as the start. And if you know how to work with branching programs, you definitely know how to work with matrices. Because if you want to take a matrix power, you can just artificially do like print in log space a branching program that the accepting probability of that branching program is the adjacent matrix. So given a matrix, you just think of it as the adjacent matrix of some graph. You're given an adjacent matrix, but you can always find a graph that does that. Exactly. Because of stochasticness. It's directed, but it's stochastic. So for example, you know, maybe you had like maybe the first row was 1/4, 1/3, 1/3, 3/4. It's a 2x2 matrix. That's the first row. I mean, it's a second row. I can also write a second row. When you can just put a branching program with width 2 that like puts like, you know, 1 edge here and 3 edges here. And it will simulate the fact that we're putting 1/4 here which here and 3/4 which here. Right, so you can always do that. It's really easy. I don't want to specify exactly how, but you know, raising a matrix power is easier than approximating probability in a branching program. And let's see what relates to what. So the W, the width here, relates to what here? No, actually. The width, right? Because for every entry, like you have like one entry for every entry here. The accuracy is related to the reality. Right, that's important. The arity, which is like, why it just 0, 1? Sometimes you want it not to be 0, 1. That's related to kind of t, the precision. Like the arity is 2 to the t, or to get precision. Like in one quarter, I needed 4 of those, right? You work in like multiples of 2 to the minus t. And the length is related to what? And like the power that you want to raise it. It's the same there all the time. Just a to the n. And epsilon is epsilon. Right? Probability, if you want that, then that's the way you constructed this branching program is really just, what's the probability of getting from here to here. And the arity is like how many edges live in our vertex, and that corresponds to the precision that you want to work with. Because you have numbers here, and you want to spread edges such that their sum is 1, like their sum is normalized sum is 1, and there is a way of writing it like formally, but it's really confusing, so I don't want to say it. Okay, so but do you kind of agree with me that Nissan, what it does is it gives you it gives you paths before we saw the branching program, right? It gives you like go according to that symbol and then that symbol and then that symbol. Given a branching program, it determines a path. But say sigma is 2. Nissan will give you go 0, 1, 1, 0, 1. That's true for any PRG. Yes, that's true. Yes, but Nissan in particular does that. And then if you are looking at a good age and you are averaging over x, not that one. Yeah, good. So Nissan did it like several times, right? The Nissan's PRG, not the BPL is in SC. Right. So I mean, every seed, if you think about it, every seed in this language translates to a matrix that from every vertex you tell me to which vertex you arrived. Right. Every seed determines a path. So starting from a given vertex, you reach to one vertex at the end. So depending where you put your vertices in the beginning, the end, rows or columns, you have like in every column you have 1 and many zeros. This indicates that if you start at this vertex, you end at that vertex, according to that seed. Every seed is a path. And what Nissan tells you that if you take the expectation over x of these matrices depend on x is the path, then this will approximate a to the n. So it gives you a bunch of matrices, a bunch of paths that when you translate to matrices, having the graph, after you have the graph, you can translate them to matrices, take their sum or average, and you have this. So it doesn't, of course, it looks like the graph, the matrix, or the graph after you translate it to a graph, but in a very mild way. Because this is a more interesting problem, really. It's more, I mean, raising a power matrix is, for the case of stochastic, it's essentially equivalent to derandomizing BPL. If it's Hermitian, there's something with the quantum stuff. I mean, it's really a more basic problem. Only the step like with the branching program, you randomizing that. You don't need the matrix. Right, that's true. Right. Good. So for every seed, let me do it more carefully here. So for every seed, so a seed is a short string, but if you apply the PRG with some seed, you get a much longer, let's say sigma is 0, 1 for a second. You get a much longer string, length n string, and that string has nothing to do with the graph, the branching program. But now, given a branching program, it determines a path on the branching program. So you go first 0, then 1, then 1, and so forth. You reach from every vertex you call a start vertex to some vertex. And you can write this as a matrix if you want. You don't take that as this matrix, which at column U, if you multiply from the right, that's the best way. Column U, you have like 1 at V and 0 otherwise. for other you will have some other vector like that, and that's per seed. Now, when you average over the seeds, X is the seed, right? So this matrix depends on the seed because the seed is like the path. I mean, the PRG takes the seed and blows it to a path. So for every X, the PRG blows it to something that induces this matrix. When you take the average over these matrices, you get this thing. I mean, you get a to the n plus minus epsilon 10 and 3. Because that's the definition of a PRG, like I'm approximating the distributions. Is it clear? Yeah, well, I can't say yes because it will offend you. It's supposed to work, yes. I mean, because you fix I and J. What the PRG tells you is that if you listen to me and go over all seeds and go over these paths, nothing is clear when I do like that. Matrix kind of like the walk matrix. Exactly. Exactly. Yeah. So that's the point. Good. Yes. So you start with a matrix. You think of it as a graph because Nissan works that way. Just kind of a AC/DC adapter. You take the graph. This is whose adjacent matrix is that. There are many graphs, but I'm choosing one. Now I let Nissan run, and he produces paths which I translate back to matrices, take their average, and then I get back a matrix. And if you do that, then that will require well, I mean, that's a randomized algorithm. If you de-randomize it naively, you would get an algorithm that runs in this space. Again, I'm not exactly sure about T, but let's see. Runs in this space that solves the problem that you asked to solve. You will solve it much more easily without the PRG. But I'm just saying that it does that. Sorry, it does that with this amount of randomness. This is the randomness he uses. That's the seed for Nissan. But the point is that the space is actually only that. So this is the seed for Nissan, that we all understand. We never really talked about the space, but what I'm claiming is that the space of Nissan is much better than its seed length. Because think what it needs to do. Let's think about it for a second. Nissan, it operates like, maybe if you remember this tree that we have, you have like you have H1, H2, H3 here. And when we moved left, it was X. When we moved right, it was H1 of X. And then you had H2 of X, H1, H2 of X. And then here we have like H3 of X, H1, H3 of X. I'm probably going to get wrong some point. But this is like H2, H3 of X, and this is H2, H1, H2, H3 of X. And that's what it actually outputs. If you open the recursion, that's what's going on. And if you ask me, okay, what's written in the so-and-so bit, I can just look at the bit what's written in this leaf. I can look at the bit representation of the leaf, figure out which H's I needed to invoke in order to compute. Like moving right, I'm invoking the H, moving left, I don't. And that you can do in logarithmic space. You don't need to spend as much as space as the seed, right, in order to answer this question. Because you have like log and things, you reuse the same space. Every application of H is logarithmic, everything is logarithmic. So there is a thing here that the space in your algorithm, it's not going to be the case. You're going to have this space for your algorithm. You don't have seed, it's not random what you're doing. So what Nissan does, it produces a randomized algorithm with a large seed, but with a small space. Do you get that? Because that's the PRG. Forget about the analysis. That's what it looks like. And I know, now looking at it, I know that I can compute every output symbol in logarithmic space. Because you tell me the output, you tell me which output symbol you want, say this one. Then I can tell whether I should act according to H1 or identity, and then according to H2 identity, and so forth. And each such action is logarithmic in space, and you reuse space. Applying H to X is logarithmic in space, and then I'm reusing the same space to apply now the other H and other H and so forth. So you can do it in logarithmic space. Yeah, good. So Good, good. That's a good point. So having h's, that's an amazing point. That's a crucial point. Having h's fixed, that's in logarithmic space. You're right. H costs this space. You're completely right. But having H fixed, I think of it as like for every H you have a little PRG. So this every such PRG, you can do it in log m space. That's a good point. I mean, that's how I think about it. I think of H as given, and now I'm working with X. But I should say that. Okay. So Saks and Zhou, what they did. So let's ignore epsilon, just to make it clear. So what Saks-Zhou did, so Nissan did this thing. So at the end of the day, he obtained, so ignoring epsilon and t, he obtained this space, like an algorithm, a deterministic algorithm with this space for solving the problem, a to the n. That's Nissan. It follows from Nissan immediately in this sense. And what Saks and Zhou did was to do this thing. That's what we'll see. And like a couple of years ago, we and other group at Harvard improved that to log n plus square root of log n. So we got rid of one square root log n. So it's better because you see you don't have here it's like log n to 3/2 times square root log n log w, and you have log n plus here. This weird scribbling w. Yeah. The other thing. So the point is that even if w is like square root, like 2 to the square root of log n, it's still optimal. Log n is optimal, so it's still optimal. But that's more difficult, and it's in the papers that you can cover. So for you, that's for you to do if you want, and we'll do this thing. So I don't remember my authors. Yes, Berlo, Tashma, Doron. Yeah. And there's another paper by, it's kind of a confusing story. We published, and then they published something on using that, and then we published at the same time. So let's think of it as the same paper. So two really bright students from Harvard, Pine and Puterman. You'll see it in the list. I think we talked about it also. Okay. So let's do this. It's really cool. Let's just raise a matrix to a power without too much space usage. And let me tell you the idea first. The idea is to utilize on the fact that Nissan has this much better space compared to SID. I mean, space after fixed the SID. So what we are going to do is we are going to okay. So let's call n 2 to the r because it's easier like that, like the j from before. And let's split r to r1 times r2. Eventually, it's going to be square root of log n h, but let's keep it like that. It's more instructive. And what we are going to do is we are going to do the following. We are going to take the matrix that we were given. No, this is square root log n and square root log n. Because the r is log n. Yes.
This algorithm would be approximating the matrix, or
no, the power.
No, I mean the power of the matrix.
Yes, it will, but not in a naive way like I just did. Yeah, it's going to be interesting. So okay. So what we are going to do is we are going to use Nissan. I'll draw it more carefully in a second, but we are going to use Nissan to approximate that. And again, so there is this h and x. So we are going to use Nissan. So for any fixed h, you get some approximation. Right? You can do it in efficient space, but for every fixed h, you can get an approximation of a to the 2r1. I want to get a to the 2 to the r. let's start here. And then I'm going to, one silly thing to do is to take another H, so this is H1, to take another H, it's the seed for, like, okay, so H is like, in Nissan, H is a vector of H's. So H1 is one vector like that. You need R1 of those if you know. Now you want to raise it again to the power of 2 to the R1, this thing. So you can try to do that. This is kind of an estimation, right? You can try, I don't know where to put the tildes. You can try to do this with H2 and proceeds like that R2 times. If you think about it, you need R2 times to do it. But you'll see you gain nothing because it's, different H's, it costs you the same. It's like instead of doing a binary, you do large arity. You raise it to the 2 to the 1, and again, it gives you nothing. So what Saks and Zhou do, they say, we are going to use the same H. That's crazy. It shouldn't work. It should not. It can't work. You can't use the randomness here if the matrix moves every time you move the randomness. Right? If this is a fixed matrix, you can use randomness. So Nissan uses H and X, right? So Nissan.
Think of A as matrix or
Yes. So what we just said is Nissan has this property that for most H's, if you take the expectation of an X, no, it's a kind of an algorithm, kind of a function of. So Nissan is a PRG really. It doesn't do matrix powering, but you can use it to do matrix powering via what we said. And for every H, so it's really actually like Nissan of given A and H. What this does, it gives you a bunch of matrices. If you take the average of those matrices, you get something which is close. Oh, you also give it like how many? You get something which is close to A to the N. So when I write that, I applied Nissan's algorithm, which comes from Nissan's PRG. I got this matrix, it depends on H. It averages over X, so I don't see X. Okay, now this matrix I want to, again, feed to the same algorithm. Again, with the same H, which is impossible. So that's actually not what they do. It is actually what we do later, but that's not what they do, more or less. So what they do is they say, I'm going to, before doing that, which is inexcusable to try to do that event. You need to be like either very smart or it's like queen sack in checkmate. You don't if you let the queen die, either very smart or not. So same thing here. So so you need to do something to this thing so that this H, so that this thing will kind of obfuscate H. So you won't see H afterwards. And that's what they do. So they take this matrix and they say, well, I'm going to shift every entry a little bit. And hopefully that shift will remove the dependency on H. Shift and truncate. Won't ruin too much the right accuracy because you can just zero up all the entries. Yes, good. Right. So let me more precise about that part for a second, and then I can write the algorithm. So say you are given this, say you have a, okay, maybe let me be a bit formal and then I'll say what's, say you have like two numbers, Y and Z. So this is a lemma in the picture. So say you have Y and Z in 0, 1, say, and they're close. And for the rest of this part, let me do close like that, to the minus 2t. T is going to be a parameter, and it will be nice that this is quadratically smaller. And now think of like a larger scale where the difference here is 2 to the minus t. Okay. Now, what I'm claiming is that for every L that's smaller than t, it's 1. The probability that if I'm sampling Z, well, I'll just write it and then I'll explain. So what am I doing here? I have these 2 points y and z, and I'm sampling. I want to kind of shift them at random a little bit to move them. So the way I'm doing it is as follows. I'm choosing z, a number between 0 and 2 to the l, maybe minus 1. And I'm shifting each of them. You see y and z. This is another z. I'm shifting y and z by quantity of that size, z of the quantity of that size. And I'm never exceeding t by doing that. I'm choosing L like that. And what I'm claiming is that they will fall in the, like, sorry, and this is the t truncation. I just truncate the last t bit after the t bit. So what I'm claiming is that they will usually be the same. In pictures, it's easier to see. If you have 2 things which are close. Yeah, sorry. Yeah, good. Yeah, so you got it. Good. So if you have 2 things that are close, and you shift them a little bit, but you don't shift too much. You don't go more than 2 to the minus t. When there's only one problem. The problem is that you shift them in a way that this would be in the middle. Right? That's a problem. That's truncation means what bin you are falling. And that will happen will be at most 2 to the minus of.
So they're closer than like the gap. Right?
Yeah, it's like, one person is complaining about my proofs, the other is about the drawing. Yeah, so it's this thing. Yeah. Yeah, so they're very close, like quadratically more than that, and usually they will fall in the same bin. Why do I care about that? So think of this as something ideal that you are trying to approximate, and this is the output of your algorithm. It's randomized output. You are guaranteed that it's very close, but it's not the same thing. So looking at y, you may learn thing about the randomness that was used to produce it. Looking at z, you cannot, but looking at y, you can. So the idea is to say, well, I'm just, before that, one idea is to just truncate to the first t bits, because if you know that the accuracy is like 2 t bits, to the minus 2t, when truncating t bits usually won't hurt you. It will hurt you exactly when you're like that. So what we're doing is instead of truncating, we're first shifting and then truncating. And the point is that, if we shift the probability that these will fall here, or maybe they started here, the probability they will stay there is really small. It's as small as the number of random bits we invest. Yes.
When you're doing this, so if you look at the random H, you get like a serial, like you could build a really bad H that could move you.
Yes, exactly on the boundary like that.
But because the step.
Exactly. So when I do the step and truncate, of course, where I get to depends on z, but except with this probability, it's not depend on the randomness that was used here. That's a crazy idea. It's a really smart idea. And you can do it for matrices, right? For matrix, you just have like W squared entries. So you shift all of them with this by the same shift. By the union bound, an entry will fail, like this won't happen except for to the minus times W squared or something. So you can also truncate and shift and truncate matrices. And then this leads to their algorithm, which I can write now, which is one of the crowns of pseudo-randomness. So it's 3 steps. And again, when you write a space-efficient algorithm, you write it regardless of the space. You write given M, or you write a 4. There are no 4s. When you go to implement it in space, you don't do that. But you can't write. We are humans. We have to write it like humans and then handle the space. So the first step is very easy. And for some reason, I like to use M instead of A, so I'm just going to do M now, okay? So we are going to define M0 tilde to be M. That's the input matrix. I don't know why I'm stick to. Also in the paper, I saw that we switch immediately from it after the introduction for no good reason. So you have this. It wasn't good. It's my point. So I goes from 1 to R2. We're going to do it R2 times. And we're going to do the following. So we are going to define Ni. This is for Nissan. So what we are going to do is we are going to use Nissan. So I'm going to use a little bit of slang here. such that it gets in as input. Again, space-wise, you need to be worried about how you do it, but mi minus 1 tilde, and it gets h. There is an h sitting there also in space, in space, in like on the box, in some tape. And okay, maybe it's just 2 for us. It also gets 2 to the R1. This tells this one approximate this matrix to that power using H. Yes, exactly. So it only averages over the X. Right, it's actually a vector. But it is a vector, you're right, of length R1. And also, Nissan needs, I don't want to be too, but Nissan needs, like, I need you to tell me what are the accuracy and confidence. So let me keep track of them a little bit, and then. But now it's complete. So now, given these demands and the H you want me to use, I can raise this matrix to that power, approximately. Good. So that is like the Y. You see, it's a matrix, it's not a number, but it's something that reveals information about H. So now what you are going to do is to define mi tilde to be, so you're going to take ni, exactly like we did here, but that's now ni. And you're going to subtract zi. So zi, we are going to have this, we need some extra randomness to do those random shifts. So we are going to have also in the tape, in the random tape, z1 up to zr2. We have R2 of those. And, times 2 to what's written there. And, it's a matrix, so let me write J, like the all ones matrix. I'm shifting everything by the same quantity. And return MR2 tilde. That's it. It's crazy. Use the same H again and again and again. But that step, with the shift, of course, make sure that the H kind of disappears with high probability between iterations.
T is constant below
the T is constant. Good. So T is a parameter, important parameter, which we need to talk about. T is the accuracy of the right, but I need it to be like the M that I need to be large sometimes. So T also need to be slightly large. Right, but it's the accuracy. It's what you assume you're given. Right, it's like log of everything, really. Log also n, because epsilon deteriorates with n. So right, so it's log n w over epsilon. But let me just keep track of parameters. You have T and L. L is going to be T or T minus 1. I just take it the largest I can. Doesn't really matter. But you have these things which I'm not specifying for a second. Let me just kill the suspense. I don't remember what that is. And you have also, of course, R1 and R2, which you don't know, which I need to figure out what's the best way, if any, to get something. So let me show you how we are going to analyze this thing. I mean, it looks like a mess. There is no way of analyzing it. Because, forget about the Nissan. There are these truncations. So it's not even, right? So there are so many problems with this algorithm that you need to be careful about how you analyze it. So the way you should think about it is as follows. So this is M0, or M0 tilde is the same thing for us, like what you get. And you're going to do 2 steps. You're going to do Nissan to get N1. Right, so Nissan, what it tries to do is to use H. I mean, it doesn't want to use H, but it uses H. But you should think of it as an H-dependent approximation of this power. That's what it kind of does. It uses H, but it approximates this thing. And when you do the truncation, this is going to make sense in a second. When you do the truncation to get M1 tilde, which hopefully is independent of H, but we don't know that yet. Potentially it does depend on H. Good. And it's, sorry? Yes, good, also, yeah, disease. Right. And when you do it again, right, you do Nissan, you on this matrix, of course, with the same H. Shame on you, to get M1 tilde of 2R1. And then sorry, I really do want one more floor. And then you're doing M2 tilde, which is the shift, like this part is the shift and truncate. Like you just shift a little bit, and as you said, it's like actually depending on H, Z1, Z2 here. Now, let's do the thought experiment where, I mean, you see, even without Nissan, we are not really, as you said, we are not really taking the power. We are taking the power of 2R1 and then do the truncation, and then you do a shift and truncation. Then you take another power of 2R1 on that and shift truncation. So even without Nissan, it's not really going to be quite exactly m to the 2n, m to the n. So let's consider as a thought experiment what would happen if you put here mi minus 1. If you right, exactly, if you don't do Nissan. But let me just define it here, and then we'll draw the picture. And then we'll have one lemma to prove, and we're done. It's kind of surprising how quick this is. Well, depending on the pace we do it, but later one-page proof. So let's define. I can define it here also, but okay, let's define it here. So let's define a sequence of mi's. There are no mi's. It's a new sequence. So it's really just doing that to the previous mi's. So mi is mi minus 1 to the 2R1. So instead of doing Nissan, I'm doing an actual powering of a matrix which I just invented. A complete bit of accuracy. But now it's going to be, right, so probably you can say like at most 2T or something. And then I'm going to use the same ZI. These are depending on the ZIs, but not on A. 2 to the minus TJ. Let's define these. So in picture, they will look like that. M0 tilde is here, and then you are going to do M1. So then you're going to do, right, so M1, so if you would have done this is the actual power, and M1 is, so, okay. No, this is the actual power. I'm defining, and I'm just defining it. It's not n. Sorry. No, I'm fine. It's fine. M0 n. Right, in the beginning it's the same. Yeah, I want it to be called like that. You see in a second. So M0 tilde is really, you're right, it's tilde, so, but it's really M. So this is really the actual power of M to the 2R1. And if you think about M1, it really does the shift and truncate with the same Z1 that was used here. Let me be even more suggestive. And then we are going to do it again. We are going to define M1 to the 2R1, take out the right power, and then do the shift and truncate. Oh, well, never mind. Shift and truncate with the same Z2. And what do you think I'm going to claim? Exactly. So this is equal to that, and this is equal to that. Equal. Yeah, no, it's critically equal. Yeah, right, we have probability. That's true. But that's the important difference between accuracy and confidence, by the way. No. No, because there could be lying in different places to begin with. If you don't shift, but they may always happen. It's not low probability over your algorithm. It's over low probability of how you believe the world should act. Like, someone can destroy you. And even if it destroys you in one iteration, you're dead in the world.
So we show that the type of probability they are equal, and then we show that the M1s are very close to the actual result, the actual value, without the shift and the target.
Yeah, once we show that these are close, the shift and target will make them equal. Right, so it's enough to show that these two are close, like better than 2 to the minus 2t, what we did in the lemma. No, you can, yeah, right. Good. That's afterwards. That's actually also easy. It has nothing to do with anything. It's like, it's a question about numbers. What happens to it's in the homework really? That's a question of the not so easy, but you know. But it has nothing to do with pseudo randomness. It's like a numerical analysis, and this is like that's amazing. We showed that these are close with high probability, sufficiently close that shift and tricate with high probability will make them equal. And equal is very different than close, right? Because it's revealed versus non-revealed. It's like a binary thing. Reveal information or not. So let me just do that proof. It's a it's a really short proof, but let's see if I'll manage. So here's the lemma. And the rest are details. I mean, once you have that, you're fine, but maybe I'll do the details next time. So the lemma tells you that for every I, okay, I want to put just for every I, mi equals. Okay, so the probability that for all j, I just want to talk about mi and mi tilde, but I really want kind of induction. So I'm going to do like full induction. So for every I, it holds that for every j smaller than I, mi, or let's do there exists a j smaller than I, for which we are in a problem. This is a probability at most I times something, and I know what that something, so let me just write it. It's this thing. So that's a claim. That's the main lemma. It says that you probably want to see something simpler. What's the probability that they are different? But for the induction, I need to kind of assume more. So I'm going to prove the probability that yes, roughly like triangle. Yes, same thing. Yes. So right. So the probability for every I, the probability that I failed at some point until the ith level is small. You should think of it as small. Well, depending what's written here, but you should think of it as small. So let's prove the lemma, and next time I'll just finish with the analysis. But it's really the lemma that's the most important one. So that's what you want to prove, right? That at the end of the day, you want to plug I, which is R2, and say that all of them are okay. Okay, so for that, we need two things. We need to define kind of to have a way of writing, so okay, so I'm going to define this set, good IZ. Z is the vector of the ZIs, ZJs. These are all the H's, such that H is good for Nissan. So that Nissan, when I plug the imaginary mi with H minus mi to the 2 to the R1, okay, so what's written here? So I'm going to look at all the good hash functions for iteration high. So what do I mean? These are hash functions so that if you're going to apply Nissan to your made up mi, it's not in the analysis, not in the algorithm, just in the analysis. So I couldn't write like ni, it's not ni. Right, so good. So let's so I write it here, and I wasn't sure I want to write it. I want to give the spot site to H. So mi are going to depend on the z's and also this set, but not on the H. So I'm kind of hiding z dependencies. But they are there. Mi depends on z. So that's exactly right. So you give me the z's that you used to compute mi, and that's good IZ1, good IZ. I mean, mi depends on actually z1 up to zi, really. But it's independent of zi plus 1. But just ignore the rest of the zi0. They're just not going to matter. So it's a kind of a thought experiment. If I were to apply Nissan to mi using H, would have gotten a good like the right accuracy, which is guaranteed for Nissan. It doesn't really exist anymore. And let's define EI to be all the problems in the world. All of the ZHs such that either there exists a J smaller than I such that MJ tilde is not as equal to MJ, or H is not in good zi minus 1. So here we have a little bit of hindsight and defining the set of problems, the set of bad strings, z and h. Like, so what's written here? These are all the strings for which something bad happens. So either using these strings, I already failed before, I want to prove that they are equal. So there is a j smaller than I for which this holds. And another bad thing I want to avoid, so I'm putting it in this set, is that h is not good for I minus 1. And I say exchange the. You will see why in a second why this is a good choice of all the bad things in the world. But this is, all the strings that made. No, that's not going to.
It's not all the bad things. It's not the bad things for the j lower than I for the h.
So.
What do you mean to put the j?
So it's like.
Exactly. So I'm saying the ones that are bad for I minus 2.
Yeah, but that kind of comes here anyhow. If that happens.
What did you say? This and I?
No, here is the set of all beds. It's a set. It's a set of all strings, all random strings, ZH, all the choices for Z and H, for which this will hold. I mean, given Z and H, I know if this holds or not. And I'm just collecting all of the bad things. Let me just do it's just that long, and then it makes sense, because you actually should see that in the proof. So let's see. So we are going to bound that by bounding this, a condition on E not happening, and adding the probability that E is happening. Is it okay if I'll see like 3 or 4 more minutes? Because it will be a shame to start that again. So I'm claiming that this is a bound on that. That's kind of a standard thing. You condition on it not to happen, and then you add that. Right? So follows by the, you should add times the probability of this not happening, but smaller than 1, and so forth. Now, what's the probability of E? I. So the probability of EI is, it's kind of by unit bound, it's either probability of this or that. So this thing is at most, so if we call this delta I, just so that we can keep track of things, this is at most delta I minus 1, right? That's exactly delta I minus 1, what's written here. Plus, no, this thing I just wrote that, right? And this is the induction hypothesis, right? So I mean, or using the names. So this is the bounded by delta I minus 1, and what's the probability for any fixed z's? What's the probability that h is not good? Like by definition, delta n, right? Nissan. Nissan tells you I don't care what matrices you're trying to approximate or why, I'm going to succeed with high probability. So the only thing we need to bound is really this thing. And that's good, because this thing, you condition on EI not happening. So it means that all the previous matrices are fine, and H is good. What can go wrong? So this means, so this event is exactly the event that, here it's written up to I we failed, but we conditioned that up to I minus 1 we didn't. So it's saying that mi tilde is not mi. Condition on mj tilde to equal mj for all j, smaller than I. And I know that h is good, because I got rid of those bad events. Now, in the picture, you can immediately see we're fine, because let's take this for example. This is like I or I minus 1. You know that the m tilde, your m tilde is, that your m tilde equals m. So maybe you do this. You know that m tilde equals m at some level, I minus 1. This is like I minus 1. And now you want to argue that mi plus 1 tilde equals mi. And that exactly tells you that, because it tells you they are the same. and H is good for this step. This means that this is close enough to that. The good means that this is 2 to the minus 2t close to that. That's how it shows epsilon in this one. And once you have that, the lemma tells you that they are equal with high probability.
So let's look at and the lemma.
Right. So the lemma was the lemma assumed that if they are 2 to the minus 2t close, then, and when my epsilon Nissan, I wrote it and erased, it's 2 to the minus 2t. So when H is good for that step, it means that this is like 2 to the minus 2t close to that. And then the lemma about the shift and truncate immediately implies that these are the same. And up to confidence, right? First, right. So that's where you use the confidence. So you have this here, and then you have plus 2 to the minus L. That was written in the lemma. So really what you get exactly is the delta I is at most delta I minus 1 plus delta N plus 2 to the minus L. It was for numbers, so you need to do it for matrices. It was like per number, unit number matrices, and then you immediately see this. Because, you know, just you get delta I is most I times this one. Because it's like a linear thing. Delta I is delta I minus 1 plus the same thing. So next time, hopefully you got that. So next time we'll just analyze the parameters and also do the small little thing that you need, because this is not exactly A to the N. It's like truncations of things, but that's just an exercise. And then we're going to start doing something very different, very beautiful. We're going to do Kakea sets and stuff like that. Kakea sets. You'll see. Amir, don't tell Amir you don't know. It's his student that did it, so.
Said something like quotations of like lines.
Exactly, right. You have like a line in every direction. Right. It's used for mergers, which we'll start doing next time.